Okay, so without further ado, we're going to open a conference with the talk of Sam Payne on enumerative problems in moduli space of curves and graphs.
Thank you, June. Thanks so much to the organizers, also Dave and Leo, Paulo, for bringing us all together. So grateful to be here. A conducive, inspiring environment. And almost all of what I'll say is based on joint work with Sam Canning and Hannah Larson and Thomas Philbacher. So some, all of us together, and some in subsets over the last 2-3 years. So let me start with an enumerative problem. So I want to count curves of a given genus over a finite field. So we'll look at the number of smooth projective curves of genus G over a finite field of size Q. And I'm going to count these up to geometric isomorphism. So I'll count two curves as being the same if they become isomorphic over FQ bar. We can just start counting these things in low genus to get a feeling for what's going on. So let's start with genus 0. There's only one geometric curve of genus 0, it's P1. So N0, so we'll think of fixing G and view this as a function of Q. So N0 is 1. So then we can go to N1. So geometrically, every curve of genus 1 is classified by a point on the J line. And J invariant comes from a curve over FQ if and only if the J invariant is in FQ. So N1 is Q. And you can do N2, and you could think the canonical linear series on a genus 2 curve realizes the genus 2 curve as a 2-to-1 cover of P1 branched over 6 points. And any 6 points will determine a genus 2 curve. And so you can start counting configurations of 6 points and look at how PGL acts. And without too much trouble, you'll find that N2 of Q is Q cubed. And these two, N1 and N2, these are special cases of a theorem of Mark Kissen and Gus Lehrer from 2002. So you could do the analogous count for hyperelliptic curves. Okay, so genus 1, genus 2, everything's hyperelliptic. And so HG is Q to the 2G minus 1. So not too bad to count hyperelliptic curves. So now you could count genus 3 curves, and genus 3 curves come in 2 flavors. There's the hyperelliptic curves and there's the smooth plane quartics. And so you could apply the same strategy. So we know we're going to get Q to the 5 from the hyperelliptic curves. And well, it's 6-dimensional, so it's going to start with Q to the 6. And so the answer is Q to the 6 plus Q to the 5 plus 1. The Q to the 6 plus 1, those are the smooth plane quartics. And 4, well, so genus 4 curves are going to come in 3 flavors. So there's the hyperelliptic curves, which will give us a Q to the 7. There's the Petri special curve. So a curve that's of genus 4 that's not hyperelliptic is a 3-to-1 cover of P1. Most of them are 3-to-1 covers in 2 ways, but some of them are 3-to-1 covers in just 1 way. Those 2 pencils can collide. And you might know that a canonical embedding of a genus 4 curve that's not hyperelliptic is a complete intersection of a quadric and a cubic. So in particular, it lies on a unique quadric. And the ones that have only one gonality pencil, those are exactly the ones that lie on a singular quadric. So to count those that are Petri special, that have only one gonality pencil, we're counting curves on a quadric cone. And you can count them. It's not too bad. You'll find that there's Q to the 8 of them. And now you're left with counting smooth curves of type 3 geometrically on a smooth quadric, which is geometrically P1 cross P1. And you'll find that you get Q to the 9 minus Q to the 6. So there's your answer for genus 4. And you might be worried that I'll go on and on like this and we'll get an 11 in an hour from now. But in fact, none of the other functions are known. Okay, so we don't know N5.
Still have a question mark.
That's the same.
Oh, that's a 7. Oh.
2 times 4 minus 1, hyperlink. Okay, so nevertheless, we can say things about this function. So this is a theorem we posted just a few months ago. So here's the theorem. So NG is polynomial. And if that sounds too good to be true, it's because it's not true. So if, okay, and only if G is less than or equal to 8. So there's 4 more polynomials that we don't know, and 5 and 6 and 7 and then 8, and then something else happens. To tell you what happens. And so N4, so all of this was relatively easy. N4 has been known for about 20 years. And so what has happened in the last 20 years that lets us make progress on questions of this type is that we have a better understanding of the unstable cohomology of MG. So maybe now let me say something about stable and unstable cohomology. And I guess as first talk in a workshop on enumerative geometry and combinatorics, I should say something about the Grassmannian. So let's start with the Grassmannian, which is a classic example of stabilization of cohomology. Slightly simpler moduli space than MG. So moduli space of k-dimensional subspaces of an n-dimensional space. And the modular description gives us a universal bundle, a topological bundle. And so this is a subbundle of trivial bundle of rank n. Okay, and so then the cohomology of this Grassmannian is generated by Chern classes of this tautological bundle. So, and of course, with some relations because the cohomology is finite dimension. So here, so Xi is the Chern class. And one way to think about these relations is that, well, this subbundle sits in a short exact sequence with the quotient bundle and the trivial bundle, and that gives us a relation on the total Chern classes. So C of E times C of F is the total Chern class of the trivial bundle, which is 1. And so this gives us a presentation with more generators. We should throw in the Chern classes of F, but these relations will allow us to eliminate the Chern classes of F, and it will leave some relations among the Chern classes of E. And these relations, you'll find that they live in higher and higher degree if you fix K and increase N. And so this stabilizes.
What's F?
So F is the quotient bundle. So this stabilizes with K fixed as N goes to infinity to a free polynomial algebra on these Chern classes. And the stable range is something like degrees less than or equal to n minus. Okay. Maybe I should also say, we can say much more about this cohomology ring, of course. So there's a basis given by the closures of the Schubert cells. And these Schubert cells correspond to partitions. Well, okay. So we could say something about point counting on this Grassmannian. So the analogous an enumerative problem would be to count FQ subspaces of FQ to the n. And we could do that by just stratifying our Grassmannian, taking a disjoint union of Schubert cells. And so this is going to be the sum over partitions that are contained in a k by n minus k rectangle. And then each Schubert cell is an affine space of dimension equal to the length of the partition. So that gives us a nice polynomial expression for the point count, but also these Schubert cells, their closures form a basis for cohomology. And so the coefficient of Q to some constant is going to be the corresponding Betty number. So this is sum over J, 2J. 2J is the 2Jth Betty number of the Grassmannian. And maybe we should say something about how big this cohomology ring is. So the dimension of H star. So we have the Hardy-Ramanujan estimates for the partition function from 1918, first application of the circle method. And so we're going to get some sub-exponential bound in this n. So it's growing like c to the square root n. So this is where k is fixed. K is fixed and is increasing to infinity. Okay, so now let's try to understand the corresponding story on MG. And one of the things we'll see is that MG is just topologically more complicated than the Grassmannian. But we could once again use the modular geometry of MG to create cohomology classes. So now our tautological family is not a vector bundle, but it's the universal curve. We can make cohomology classes out of its geometry. So on the universal curve, now we have a tautological line bundle. So the line bundle would be the relative canonical bundle. So the fiber over point will be the cotangent bundle of the curve at that point. And this line bundle has a term class, C1, and then we can apply operations. So for instance, we can take powers with respect to cup product, and then we can take Gießen push forward. So we can integrate along the fibers, and that will give us a cohomology class. And so this is the definition of the Miller-Morita-Mumford kappa class. So kappa I, so in degree 2i. So this would be the analog of xi. And there's a inspired and inspiring conjecture due to Mumford. So this was 1983. So Mumford conjectures that the cohomology of MG stabilizes as G goes to infinity to a free polynomial algebra now on the infinitely many kappa classes. So at the time that Mumford made this conjecture, we knew the cohomology ring of MG for exactly one value of G, so for G equals 2. And the rational, so M2 has the rational cohomology of a point. So that's how much data went into this conjecture. And this conjecture inspired a great deal of activity, and it's true. So it's a theorem. It was proved through the work of many people. So John Harrer proved that the cohomology stabilizes. Ulrike Tillman proved that it stabilizes to the cohomology of an infinite loop space. Madsen and Tillman made a conjecture about which infinite loop space it should be. So it should be the infinite loop space of the one-point compactification of the Grassmannian of affine real two planes in R infinity. Okay, and then you can apply techniques from stable homotopy theory to compute the cohomology ring of that infinite loop space, and it does agree with Mumford's conjecture. And so that prediction is what finally Madsen and Weiss proved in 2007. Okay, to establish Mumford's conjecture as a theorem. And now a word of caution is in order here. So in both cases, and in general with stabilization of cohomology, so there's a map from the stable cohomology ring to the cohomology ring. And for the Grassmannian, it's surjective. So the cohomology was generated by the classes that generate the stable cohomology. That is not the case here. So the map from the stable cohomology, so the subring generated by kappa classes, so it's not surjective. So it's surjective for G equals 2, but M2 has the cohomology of a point. And so it's not surjective for any G at least 3. So that's the only case. Yes, Alan.
So you said this with the Grassmannian stabilizes because I know how to include the Grassmannians into one another and get maps on cohomology. So what are the maps that are going on between the MGs?
So the cohomology of MG includes into the cohomology of MG1, where you should think of MG1 as having one marked boundary component. And then you can go from MG1 to MG plus 1 by gluing on a genus 1 curve with 2 marked boundary components. And then you can check that the image of the cohomology of MG and the cohomology of MG1 or homology, so when you push forward that lands in the image of. So there is stabilization, but you have to work harder to get the stabilization maps. So the homotopy theorists are working with that marked boundary component and then deducing things about the unmarked curves. Good question. Okay, so this is not surjective. The image has been studied quite a lot. So the image is denoted R star. It's called the tautological ring. Studied often in relation to Gromov-Witten theory. Many facts known about this. So this is supported in degrees less than or equal to 2G minus 4. So this is work of Faber and Loyenka from the 1990s. And well, its structure is very much like the structure of the Grassmannian. So the dimension grows sub-exponentially. It grows like a partition function. That's one generator in each even degree. So sub-exponential.
What does the notation R cross mean?
This is just the standard notation. It means tautological ring.
Okay.
So if that's familiar, great. If not, you can ignore that. It won't come up again. Yes.
Maybe this is a premature question, but so how does can you remind us how the I guess cohomology over here relates to the energy counts on the original problem?
We'll get there, but for now, just think of this, that there's some relation between cohomology and point counting.
Okay.
It might be familiar if you've thought of spaces with pavings by affines.
Great. All right, thank you.
Yeah. Okay, so how do we know that there's lots of cohomology that's not in the image of this map? Well, when you cannot compute cohomology, then try to compute an Euler characteristic. And if you can't compute the Euler characteristic, then try to estimate. And that's what Haar and Zagier did. So Haar and Zagier looked at the Euler characteristic of MG. What they could actually compute is the orbifold Euler characteristic of MG. And then they bounded the difference between that orbifold Euler characteristic and the actual Euler characteristic. And they found that the difference was small enough that they have the same asymptotics. And the asymptotics is, well, there's a square root of pi over g times g over pi e to the 2g. And there's a sign. So the Euler characteristic of MG eventually alternates sign. It's negative for g even and at least 8. And it grows like g to the 2g, or like g factorial squared. So it's very much super exponential. And as Haar and Zagier pointed out in their paper, at the time when they wrote this, there was no known pair K and G where HK of MG was known to not be generated by the image of the kappa classes. So those examples came later. The first example was due to Loyenka, so 6M3 is Q. So this is in even degree, but the tautological ring is generated in degrees up to 2G minus 4, which for G equals 3 is 2. So H6 is in too high degree to be tautological. So this is something else. He also computed the mixed Hodge structure, and the tautological classes have pure weight, but H6M3 has weight 12. So as far from pure as possible. So this is 93. And then it took more than a decade to get a second example, but we finally got one. So this was H5M4, again, Q. So now it's in odd degree, has no chance to be tautological. And this was Tomasi in 2005. And until a few years ago, this was the whole list. So that was the known unstable cohomology. Yes?
How do you interpret the statement of the Euler characteristic geometrically when it grows as fast? I don't have a good intuition.
It means there's a lot of, you're asking just intuitively?
Yeah, I mean,
There's a lot of topological complexity in MG.
in terms of wrapping around itself, what is it?
It means the Betty numbers are huge. And I think yeah. That's all. Yeah, it's, yeah, there's there's quite a bit of mystery. I think, yeah, so the unstable cohomology of MG has been challenging to get at. Harrer told us some things about where not to look for it. So in 1986, Harrer tells us that, so MG is a K-pi1 for the mapping class group, and the mapping class group has some extra structure. It's a virtual duality. Okay, so it has a virtual cohomological dimension, and the VCD of MG is 4G minus 5. So this means that even though MG has real dimension 6G minus 6, any local system on MG will have vanishing cohomology in degrees above 4G minus 5. So there is something that plays the role of a dualizing sheaf that has rank 1 cohomology in degree 4G minus 5. But are also that the singular cohomology vanishes in that degree. So the trivial local system does not have cohomology in degree 4G minus 5. So the first place where one could look, so in high degree, the first place where one could look for unstable cohomology would be degree 4G minus 6.
What is VCD?
Virtual cohomological dimension.
You said the singular cohomology is 0 in that degree?
Yes. So a few years ago, in joint work with Melody Chan and Soren Galatius, we got some information about H4G minus 6. And so what we found was that that it's helpful to join all the H4G minus 6s together. And then there was some structure on the quotient. And maybe a nice way to say it is to take the dual. So this would be the direct sum of the degree 2G compactly supported cohomology. And then that contains a subspace, which is the weight 0 part. So the first part of the weight filtration in the mixed Hodge structure, that carries an additional algebraic structure. So it carries a Lie bracket. Well, any vector space carries a Lie bracket. You could take the 0 bracket, but this is the bracket that it carries is not the 0 bracket. It contains a free Lie algebra with generators in each odd genus starting from 3. Okay, and you've seen one of these generators. So 4 times 3 minus 6 is 6. And so Loyenka's class is the first, equal to the first generator. Now you can compute the generating function for the dimensions of the genus graded pieces of this free Lie algebra. You'll find they grow exponentially. So the dimension is greater than some exponential plus constant. The base of the exponential is 1.3247. This is the real root of t cubed minus t minus 1. This is actually a very interesting number. So this is the smallest p-zone number, but maybe that's a digression for another day. So now we start to see the first infinite families of unstable cohomology. They're growing faster than the tautological ring, but not as fast as the Euler characteristic. So we've still somehow uncovered 0% of the cohomology of MG, but it's more than we had before. And so I've described what we found in this 1 degree for G minus 6, but we found other classes as well. So H15 M6, which is the start of an infinite series in degree 4G minus 9. So the next one is H23 M8. And there's also classes that are in neither degree 4G minus 6 nor degree 4G minus 9. So there's in the middle cohomology of M10, so H27 M10. So all of these are non-zero. So that was coming from the weight zero compactly supported cohomology. And in more recent work, we've shown that so this exponential growth is ubiquitous. So there's similar exponential growth of dimension h4g minus k. So for 70 values of k. So it's not just about this one special place 4g minus 6. And so we conjecture, and the exponential growth is all with the same base of exponential 1.3247. Good. All right. What more do I want to say? Maybe I should say that this was not expected. So there was a conjecture of Kontsevich from 1993 that if you fix k and let g grow, then h4g minus k should eventually vanish. So those conjectures are not right. For Kontsevich, this was a finiteness statement. So he had an infinite dimensional Lie algebra connected to the associative operad that he was studying. And in hk of that infinite dimensional Lie algebra, it contained the direct sum over all g of h4g minus k. So he had a family of different infinite dimensional Lie algebras that he was studying, and he expected all of them to have finitely generated homology. And in fact, some of them have finitely generated homology, and some of them do not. So this one is one of the ones that's not. The same conjecture was made 20 years later independently by Church, Farb, and Putman. So they were viewing this from the point of view of stabilization. So they constructed a map from h4g minus k mg to h4g plus 4 minus k mg plus 1. And they conjectured that those maps would eventually become isomorphisms when g was large. And they proved that if they become isomorphisms, then the group stabilized to 0. So there were different points of view expecting behavior other than this, but this is what happens. And maybe I should mention an open problem that I like very much. So there's 1k for which we never find cohomology in degree h4g minus k, and that's h4g minus 7. So that's an open problem. Does h4g minus 7 mg vanish? And this isn't just a curiosity. So this Lie algebra that's appearing here is important in, this is the Grothendieck-Teichmuller Lie algebra. This is important in many deformation theory problems. And often when this is the deformation space, the obstruction space is a subquotient of h4g minus 7 mg. So in particular, if you prove that h4g minus 7 mg is 0 for all g, then that immediately implies formality of deformation quantization. So one of the 3 results for which Kontsevich was cited for the Fields medal in 1998. It also implies formality of the little disk operads. So there's a long list of deformation problems that become formal if H4G minus 7mg vanishes for all G. And then you would get a new connection between the topology of mg and things like deformation quantization. So it's not just a silly problem. Yes.
Can you say anything about the new classes you found? Do they have some geometric description?
They do, but if I go there, then I won't get back to the theorem. Ask me over tea and. Okay, so how are we able to make progress on the unstable cohomology? I think I've given a little indication of this, but let me make it more explicit. So we're using the yoga of weights. So all of this is based on the seminal work of Deligne from the early 1970s. And for all of this, it's going to be more convenient to work in compactly supported cohomology instead of cohomology. But we've already seen compactly supported cohomology. We're on manifold, so this is the dual of cohomology. Yes.
You're going to say a few words what unstable cohomology is.
You could think of unstable cohomology as the quotient of cohomology by the image of the stable cohomology. But in fact, we are working in degrees where the stable cohomology maps to 0. So degree by degree, there's not even a quotient that you have to take. So these are just the cohomology in degrees outside the image of stable cohomology. Not stable.
So stable means generate like something with a kappa class. What is stable?
Yes. So this is the stable ring, is the ring generated by the kappa classes. Okay, so weights. Okay, so there is a filtration on all cohomology with rational coefficients, except where I say otherwise. So we take the weight 0 compactly supported cohomology. So this sits inside weight 1. So there's a filtration on compactly supported cohomology, and the weights go from 0 to the cohomological degree. And these filtrations are canonical and functorial. So the graded pieces, so GRJ, which is WJ mod WJ minus 1. So this carries, again, functorially, a pure Hodge structure of weight J. Okay, so that's something about an additional structure, a descending filtration after tensoring with C. But you could also tensor with other uncountable fields and see other additional structures. So GRJ tensored with Q, well, maybe I should say, so let's, we're working over Q like we are for the Grassmannian and for MG. So then we have, if we go up to QL, then we have an étal to singular comparison theorem. And so then we get an action of the Galois group. So we have the absolute Galois group. So Q bar over Q is now going to act not on the rational cohomology, but the cohomology with QL coefficients. And this action will preserve W. And so it gives an action on the graded pieces. So the action on GRJ is very special. So inside the Galois group, there are the Frobenius elements defined up to conjugacy. And so the Frobenius at P has eigenvalues. So these are in QL bar a priori, but the eigenvalues are algebraic integers. And they're of size P to the J over 2. So for any isomorphism from QL bar to C, the image will have complex norm P to the J over 2. So these are very special numbers. They're called Vey numbers of weight J. And this is independent of, so you might worry about this choice of L. but the characteristic polynomial of Frobenius is independent of L. So these are all theorems of Deligne from the 70s.
So there's a lot of notation there that's not getting defined, including like W, whatever is being preserved there.
So I'm telling you that there is a filtration, and if you have any, so this is for algebraic varieties. So if you have an algebraic variety over Q, there's an associated complex analytic space, which has singular cohomology groups. There's a filtration on the rational compactly supported singular cohomology groups. And if you have a map between algebraic varieties, then the induced map, and I guess it should be a proper map to get an induced map on compactly supported cohomology. And then the induced map will respect these filtrations. And it's better than that. So if you have excision sequences, you have spectral sequences associated to filtrations of varieties by subvarieties, all of the arrows in all of those diagrams will respect these filtrations. They will commute with the action of Galois. They will induce morphisms of Hodge structures.
So W is this filtration.
W is defined to be this filtration. That's right, yeah. Now, I'm not quite yet telling you how to construct it, but I will more or less in an example in just a moment. Okay, so this filtration is, the existence of this filtration is proved using the theorems of Nagata and Hironaka on existence of compactifications and resolution of singularities. So we can compute the filtration from a suitable compactification. And for MG, we've had this compactification for a long time. So this is the stable curves compactification. And now the moduli space of stable curves, so these are nodal curves with finitely many automorphisms, or equivalently nodal curves with ample dualizing sheaf. And so this is stratified by topological type up to homeomorphism. So we could give an example, say for G is 2. So you could have a genus 2 curve that degenerates to, say, a genus 1 piece and a genus 0 piece with a self node. And so this is one topological type of stable curve. And then you could encode this by a dual graph. So you make one vertex for each irreducible component. You draw an edge for each node. So self nodes give loop edges, and you should label the vertices by the genus of the components. So this is where graphs come in, and this is so when you're counting strata, so remember in both computations of cohomology and point counting, we end up needing to keep track of strata and counting according to strata. So here we have strata corresponding to partitions. The role of partitions in this story is played by dual graphs of stable curves.
Unlabeled vertex means genus 0.
Yes, thank you. Yes. So the stratification by topological type means that MG bar is a disjoint union over stable graphs, and there's going to be some moduli space corresponding to that dual graph. So M gamma is the product over the vertices of the moduli space of curves with the genus attached to that vertex, and then the number of mark points would be the valence of that vertex. But this doesn't see the automorphisms of the graph, whereas isomorphism class of the curve does see that. So we have a disjoint union over gamma of M gamma modulo this finite group, the automorphism group of the graph. And this plays a crucial role. And now, when we want to compute the weight filtration, one of the things that will play the central role is the normalizations of the closures of the strata. So these stratas, their closures are not smooth, they're not normal. So the boundary divisors in the stable curves compactification self-intersect. Okay, so we're going to have to look at M gamma mod gamma closure normalization. And then this is M bar gamma mod gamma, where M bar gamma means put a bar here. Okay, so product of moduli spaces of stable curves quotiented by this finite group, the automorphism group of the graph. So these are the spaces that will appear in the spectral sequence that computes the associated graded of the weight filtration. So let me give some indications of how that looks. So this is a spectral sequence that degenerates at E2. And so on the E1 page, we just have a stack of rows. And each row is a chain complex. So let me tell you what the jth row looks like. So we have, so the moral that one should have in mind is that GRJ is the part of the cohomology of your variety that is a subquotient of jth cohomology groups of smooth projective varieties. So this jth row is going to be cohomology groups of jth cohomology groups of smooth projective variety. We have HJ MGR, and then we have the direct sum over codimension 1 strata. Well, the codimension of a stratum is the number of nodes, which is the number of edges in the dual graph. So we take the direct sum over one edge stable graphs of HJ M bar gamma. Okay, but not quite. We want M bar gamma modulo ot gamma. So we should take the invariant subspace for the action of ot gamma. And then the next term is going to come from codimension 2 strata, so graphs with 2 edges. And then we'll have HJ M bar gamma. And you might be tempted to put ot gamma here. Sorry. So the automorphism group of gamma is acting on the edge set by permutations, and we need to take the sign of that action, so the determinant of that permutation action, and then we take invariance. And this is because of a local system that appears in, so always in the homological algebra, the signs are crucial, and this is what it takes to get the signs right in the spectral sequence. And okay, and then all the rest of the terms are the same. Okay, so you just start increasing the edges, and at every stage you tensor with the determinant of this permutation representation, and that's it. And GRJ.
This term had the determinants of tensor square. Had you written the next one? So we had determinants to the tensor 0 hiding in the first one, and then to the third power.
No, we had determinant hiding here, but it was permuting a set of size 1. Always determinant. Okay, so GRJ of HI plus J is HI of E1 J dot. Okay, so the cohomology of this complex is giving you GRJ in all different degrees.
Is this always degenerated E2, or is this special to this situation?
It is, it is special to these being algebraic varieties.
But in the algebraic variety situation.
That's right. So we saw a bunch of theorems about cohomology of MG that were all proved using really topological techniques, stable homotopy theory. And I should say, there's no algebraic geometry proof of Mumford's conjecture still. Okay. So, but there is also a tradition of using techniques from algebraic geometry to make progress. And so here's a technique from algebraic geometry that's going to give us insights that have eluded the topological approach. Topologically, one can write down this spectral sequence. So this is the Leray spectral sequence for the inclusion of MG and MG bar. So it's a perfectly natural topological spectral sequence, but degeneration at E2 is an algebraic geometry fact. And it's just 100% proved by weights. Okay. Good. All right, so now we should study this spectral sequence row by row. So we'll start with the 0th row, right? So that's not too bad. We have H0 of all these moduli spaces. And Was there a question?
Well, I was just trying to understand the determinantal bundle, but it's residues coming from it.
Yes. Yeah, so if you do all of this via Deligne cohomology, then you're going to see this in terms of the dz's over z's. Permuting those. Okay. So if you go to j equals 0, then you have the h zeros of all these moduli spaces. And an important fact is that these moduli spaces are all connected. So you're getting one copy of Q for each dual graph of stable curve, almost. You're getting one copy of Q for each dual graph of stable curve on which the automorphism group acts by even permutations of the edge set. Okay, so that just, it is what it is. So j equals 0. So there's another interpretation of the j equals 0 row. So this is the cellular chain complex that's computing the compactly supported cohomology of the tropical moduli space. So you take dual graphs of stable curves and you put an edge length on each of them. And now the cells are not quite cells, they're orbicells. So they're quotients of open affine spaces by finite groups. And so those orbicells, some of them are orientable and some of them are not. And they're orientable exactly when the group that's acting preserves orientation. So that's another way of seeing this. And so the work with Melody Chan and Soren Galatius, we showed that this row is quasi-isomorphic to the Consavage commutative graph complex. And so that's essentially saying that if you look at the stable dual graphs that have either a vertex of positive genus or a loop edge or both, those form an acyclic, the graphs with neither of those form a subcomplex, and the inclusion of that subcomplex is a quasi-isomorphism. Okay.
What is the symbol after G for the Consavage commutative graph complex?
It's an upper G. So G has graphs of all first Betti number, but the differential on the graph complex preserves the Betti number. So the Consavage commutative graph complex splits as a direct sum over genera, and this is the genus G part of the Consavage graph complex.
For the phenomenon you just mentioned, is it important that the coefficients are characteristic 0?
Yes. All right. And so we cannot compute the cohomology of this graph complex. We can say some things about it. So there's one degree that we understand fairly well. That's the one that gave us this free Lie algebra. I should say that so Consavage studied this graph complex as a differential graded Lie algebra. So there's already a bracket at the chain level. And so that descends to cohomology. And so that's the bracket that we were looking at. What more did I want to say? So, but we can estimate the Euler characteristic. And so if you were here in the fall for the Combinatorics of Fundamental Physics workshop, so Berinsky spoke on this. So the Euler characteristic of, so the 0th row of this spectral sequence, this has a rich asymptotic, so it grows roughly like G to the G. So with alternating signs for G even, and it grows like G to the G over 2 with non-periodic signs for G odd. And here when I say, so I really, okay, not at, yes. Okay, so it's bounded above and below by a constant times g to the g over 2. And then in that range, it's oscillating wildly with chaotic signs. Okay, so there's something a little weird going on there, but this is super exponential growth. And you can think of this, as I said, so this is the sum over stable dual graphs such that the action on the edge set is even, and then you count them with -1 to the size of the edge set. So this is now a graph enumeration problem. So we're counting graphs in this way, and there are combinatorial approaches to this for various reasons. Formulas for this type of graph enumeration appear most often in the physics literature. So this is approached using Wick's theorem from quantity field. Okay. All right, so we're now I should start telling you about other rows. So E1 is 0. E1 1 dot. So H1 of MGN bar vanishes for all G and N. Now, if we look at the second row, now we're in good shape because H1 vanishes. So we have these terms which are products of smaller moduli spaces. You have Kunith decomposition, but because the H1s are vanishing, the only way to get H2 would be to have a 2 from one factor and a 0 from all the others. And so this was we've studied this row quite a lot. So in joint work with Thomas Wilvacher, and it was published just a couple months ago. There's a lot to say there, but I think for today, I'll leave that aside. You can look at the third row and it's 0 again. So that should help you get to the fourth row. And it sort of does. So a very recent theorem, so this is with Canning and Larson last year, is that H4 MGN bar is generated by tautological classes. So I haven't said what the tautological ring is for the stable curves, but it involves kappa classes, but also classes from the boundary. So just now, so this was predicted by Arborello and Cornalba. So this uses the work of Arborello and Cornalba computing H2 MGN bar for all G and N. They predicted that H4 should be tautological. We finally did confirm that. And we've made a conjecture. So I hope sort of somewhat in the spirit of Mumford. So the conjecture is that H even MGN bar is tautological for degree less than or equal to 1. And if this is true, then it's sharp. And it's open for degree 6. Okay, so so this is okay for degree 6, but we can only do it for G less than or equal to 2 or G greater than or equal to 9. Okay, so from 3 to 8, there's a window of that we don't understand. All right, and okay, so time being what it is. So now let's do point counting. So I want to return to the enumerative question that I stated at the beginning, or enumerative theorem. So how are we going to count? Okay, so now I should tell you that there's actually two different, or 2 point counting problems that look different. Okay, so in enumerative geometry, in all contexts, geometry, combinatorics, when we're counting objects that have automorphisms, then most commonly one should count them with a multiplicity that's inversely proportional to the size of the automorphism. So this is the orbit counting. And we saw that already with Harizagier, that orbifold Euler characteristic that they computed exactly, that's counting cells in a stratification that's compatible with stabilizers with multiplicity 1 over the order of the stabilizer group. And so here, the good orbicount that one should look at is the sum over all isomorphism classes of curves over FQ. Now we mean isomorphism over FQ, and we should count them with multiplicity inversely proportional to the size of the automorphism group. And then it's a wonderful remark from the 1980s by Serre, so not special to MG. So this is about orbicounting on Deligne Mumford stacks, that orbit-counting in this way for a finite field is the same as counting geometric points that come from the finite field on the coarse moduli space. Okay, so secretly, we were doing this count, but to do the low genus examples, it's easier to think about it this way. But if we think about it this way, then it has good formal properties. So this has the Behrend, Grothendieck, Lefschetz trace formula. So being defined over FQ is being invariant under the appropriate iterate of Frobenius. So Q equals P to the M, so that should be the mth iterate of Frobenius at P. And then Lefschetz tells us that we should count fixed points by taking the graded trace, so the alternating sum of the traces on compactly supported cohomology in the non-compact case. And so that's what we're doing here. But now compactly supported cohomology is computed by this spectral sequence. And in alternating sum, we don't have to pass to the cohomology. We can just compute it directly on the E1 page. Okay, and so now we're looking, well, how does Frobenius at P act on all the terms in this spectral sequence? And now I have something important to tell you, which is that everything that we've looked at so far, Frobenius at P acts by a power of P. Everything we've seen. So the unstable class of Loyenka, the unstable class of Tomasi, the 0th row, the 2nd row, the 4th row. In fact, so a theorem with Canning and Larson is that H even prob P acts by P to the degree over 2 for a degree less than or equal to 14. So we conjecture that this is true up to degree 20, but we can't quite prove that, but we can get up to degree 14. Okay, so we're not going to get any non-polynomial contribution from even rows up to 14. And so we should look at, okay, and now here's another theorem. So this is also from last year. So this is joint work with Jonas Bergström and Karl Faber, which is that H odd mg n bar is 0 for a degree less than 11. Okay, now you see why it has to be polynomial in small genus, because you have to get to the point where the 11th row shows up. Okay, now the 11th row shows up at genus 7. Okay, so you start getting M bar gammas that have H11 starting from genus 7, but they show up on graphs that have automorphisms, and H11 is never invariant until you get to genus 9. Okay, H13 starts showing up also in genus 8, but the graphs have automorphisms. So this combinatorial part, the graphs and their automorphisms are essential to the proof of that theorem. And then, okay, and now I'm out of time. Let me just say in a minute or two. So then we computed H11 mgn bar for all g and n. We showed that in fact it vanishes when g is bigger than 1. Okay, so there's a key example that's been known for a long time, which is H11 M111 bar. And the Frobenius at P acts with trace equal to tau of P, the Ramanujan tau function. So this is the coefficient of x to the P in the weight 12 level 1 cusp form for SL2Z. So there's something amazing that happens. There's this remarkable arithmetic function, this modular form that appears. And in fact, that's the only thing that shows up in H11. So all H11 on all moduli spaces of curves is pulled back from M111 bar under the forgetful map. And that was almost enough to prove the theorem that I stated at the beginning. So you want to compute the Euler characteristic of the 11th row of this spectral sequence. We have a generating function for it. And in fact, now we can prove that that Euler characteristic is non-zero for g greater than or equal to 9, except for g equals 12. Okay, so for g equals 12, it's 0. I don't know if there's weight 11 cohomology on M12 or not, but I know that if it appears equally often and even in odd degree. So then back to the drawing board, we compute H13 MGN bar for all g and n. And in fact, it's not too bad. All H13 MGN bar is a push forward of an H11 under a codimension 1 inclusion. Okay, that gives you a full presentation of H13 MGN bar for all g and n. And we do not have a generating function for the Euler characteristic of the 13th row, but we can compute it in some examples, including for M12. And that Euler characteristic is -6. Okay, so that's where the non-polynomial contribution comes from. It comes from a Tate twist of the delta 11. All right, let me stop there.
Yeah, so going back to your original theorem, I guess, is there, in what the story you've told us, is there a way to control the degrees of the polynomial terms?
Yes. So when you're on a variety of complex dimension k, then the leading term will be q to the k. And that's just the trace of Frobenius acting on the fundamental class.
Okay, so.
And then, yeah.
Can you then use polynomial interpolation, or the numbers get
Yes.
too large?
Absolutely. Yes, you can use interpolation, and yes, the numbers are too large and too hard. So you can get reasonably far that way.
But like not to N5, say?
So far, not to N5. That's right. So the number of curves of genus 5 has been computed over F2, over F3, maybe F4. But that's a polynomial of degree 12.
Sure.
So we don't have we don't have enough. Yes.
Your N4 has a complication with that negative sign.
Yes. So Tomasi's class H5M4. So Frobenius at P is acting. So the dual of that is H13 with compact support of M4, and the Frobenius at P is acting as multiplication by P to the 6. And it's appearing in odd degree. So that contributes negatively to the point count. Yeah. And when we go to M9, there's exactly one copy of H11 M111 bar, and it appears in degree 22. So the deviation from polynomiality is plus tau of P. Yes, minus q to the 6 because odd degree.
So the signs are predictable from sort of the analog of the Selby composition.
Yes, the signs are predictable, but the combinatorial things that we're counting are complicated. Yeah. Yes.
In this open problem, for what G the vanishing is known? The open problem.
Oh, good question. Up to 4.
Only up to 4.
Yes, only up to 4. It is, but then we know vanishing of certain pieces of the weight filtration for all G. So I know that the weight 0 part vanish. So if we go to compactly supported cohomology degree 2G plus 1, weight 0 vanishes, weight 2 vanishes. I think we know that weight 11 vanishes. I think we know that the holomorphic part of weight 15 vanishes. Okay, so yeah, but to actually say on the nose that this group is, and now I'm sorry, I told a lie. We do not know that weight 0 vanishes. I'm sorry, I take that back. Yeah, so weight 0 is the crucial one. We don't know. I think we do know vanishing maybe for weight 2 and 11. But yeah, weight 0 is the crucial one, and that we don't know. So this is H1 of the Conceivage graph complex. It's an open problem whether it's vanishing or not. That vanishing is known. So the vanishing of the crucial part of the weight filtration is known up to g equals 10 or 11. Yeah. Thank you. Yeah.
So I actually have 3 questions. I call it like 1A, 1B, and 2. So maybe I'll ask one first. So have you looked into if whether like this modular form could have a structural explanation from like modular curve, because like
of course, yes. But that's well known. So this appearance of the coefficients of the modular form in the point count have been known since the 70s through the work of Deligne. So this is the Eichler-Shimura correspondence. So there's going to be some local system on M11, which is coming from push forward from the 10-fold product of the universal curve. And yes, so this is all known and well understood in arithmetic geometry.
So this means that for any higher modular curve that may have higher genus, you already know that they will contribute to something.
That's right. So we know that all of the cusp forms of level 1 for SL2Z contribute to the cohomology of M1n bar. We know which n it shows up with. We know how Sn acts. Yes, all of that is known.
And then the other questions, they are close to each other. Is so one thing is that are there cases where you can get the Euler characteristics before knowing the cohomology?
Yes.
And
yeah, so already, here we cannot compute the cohomology of the graph complex, but we have pretty good control over the Euler characteristic. Also in weight 2, we have a generating function for the Euler characteristic. We have expressions for the cohomology in weight 2 in terms of the cohomology in weight 0 that we don't know.
So do they come from doing the point count first?
No, those come from graph enumeration. So we have a graphical, so I didn't say this, but H2MGN bar, everything is tautological, so everything has a graphical description. It's either a psi class associated to a marked point, and a marked point is a half edge, or it's coming from a boundary divisor, which is an edge. And so, so somehow everything can be described graphically, and you're doing some alternating some counting decorated graphs. And that's how the Euler characteristics are computed.
The related question is that in the case of Euler characteristics, are there interesting additional information in this those Hart polynomial, which is the ordering sum of this HPQI?
Yes, and what I should really say is that if you want to take this as far as possible, then the right thing to do is to think one motivic structure at a time. Okay, so you don't care just about the HPQs, but you care about which irreducible Hodge structure did this come from. And part of what's driving this progress is that we have predictions from the Langlands program about which irreducible motives should appear in motivic weights up to 22. Okay, and so that 22 is motivating the 20 that appears here. So in the predictions, 22 is the first even degree where we expect a non-Tate motive. And it'll be sim2 of that motive of weight 11, the H11 M111 bar. So that would be, so I would encourage, rather than thinking about HPQs, think about one irreducible Hodge structure at a time.
So in particular, they may not be pure. You could have like P not equal to Q.
Absolutely. Oh yeah, already on H11. So the H11 M111 bar is of type 11, 0 plus 0, 11. The Eichler-Shimura correspondence is giving you a holomorphic 11 form on M111 bar.
Oh, but I see that is not Tate, but still is the weight is like, are there cases where the weight P plus Q could be used?
Oh yes, of course. This the weight for, yeah.
Okay.
Yeah.
Is it clear what these point count polynomials mean at Q equals 1 or maybe even -1?
Good question. Not a priori. Yeah, it's a good question.
What's the question?
The question was,
What the comment?
Bhargav said, is it not topological?
Is it not the topological Euler characteristic? I thought the polynomial point boundary is just the
Add -1.
or one.
One is. the Euler characteristic.
One should be the Euler. Okay, that's fine. So yeah, so one should be the Euler characteristic. Yeah, that's okay.
Okay, so maybe we'll save further questions for the break. We're going to have